Hello everyone, I'm Katkuri Satvika presenting my Embedded Systems internship at Emertex Technologies. This internship gave me the hands-on exposure to microcontrollers and real-time system design. Today I will take you through the embedded system basics and a microwave oven project which I developed during this internship. Introduction to the embedded systems. An embedded system is a specialized computer designed for a specific task. Unlike PCs, it is optimized for low power, real time performance, and a small size. A common example is microwave oven, where a microcontroller controls heating, timing, fan, and display simultaneously. And next, coming to the components of the embedded systems. Embedded systems consist of hardware and software working together. Hardware includes the microcontroller, input devices like keypads, output devices like LCDs, timers, and power supply. And we can also see CLCDs or fans also. And software includes the firmware, application firmware, device drivers, interrupt routines, and state machines, which manage the multiple modes and tasks efficiently. Coming to the main component of the embedded systems, that is microcontroller. The microcontroller is known as the brain of the embedded system because it integrates the CPU, memory, and peripherals on a single chip. The CPU executes the instructions, flash stores the program, and RAM holds the temporary data. It is designed for dedicated tasks rather than general purpose computing. That is why it is mostly used in the embedded systems. Coming to the project requirements. First one is MPLAB ID. For this project, we used MPLAB ID, a development platform for PIC microcontrollers. And this is a ID, this is like a software which is used to develop the projects. It mainly uses the C programming so that it is very easy to learn and understand. And next, the compiler which we used is XC8 compiler. It is a human readable C compiler that converts the machine code and optimizes the memory usage and provides a built-in delay functions and which are essential for the timing control. And this XC8 controller also handles multiple files, headers, and project organization for easy hardware interfacing. So we are using this XC8 compiler, and these are the functions of XC8 compiler, like code translation, the code translation, standard compilance, header integration, optimization, and these have built-in macros. And coming to the next component which we used is the microcontroller, which is PIC16F877A. This is a 40 pin 8-bit controller with 8 KB flash, 368 bytes RAM, and 256 bytes of EEPROM. It supports up to 20 MHz and operates between 2 to 5.5 volts battery, and making it ideal for embedded applications with multiple peripherals. It is very easy to use and easy to program, and so that it is very easily integrated, so we can program it very easily. Next, architecture. When coming to the architecture of PIC, this architecture of this controller, it is containing RISC CPU. It contains the RISC CPU. It is a 40-pin 8-bit microcontroller, and it supports also. It has multiple input-output ports, internal timers, ADC modules, and a watchdog timer. A two-stage instruction pipeline allows faster execution, and timer 2 is used in this project to generate the timing interrupts. Next, coming to the peripherals in microcontroller. There are lot of peripherals in microcontroller. The used peripherals are starting from here. First one is LCD interfacing. In this project, a 16 into 4 LCD is integrated in 4-bit mode to save pins. Proper initialization sequences and timing delays are used to ensure reliable LCD operation. This is the first peripheral we are discussing. And second one is interrupts. So interrupts in embedded system. Interrupts allow the microcontroller to handle time critical events efficiently. That is, when an interrupt occurs, the MCU pauses the main program and executes the interrupt service routine, that is ISR. This helps in tasks like maintaining a 1 second countdown timer without stopping the keypad scanning. This is the second peripheral which we are seeing. And the third one is matrix keypad interface. A matrix keypad reduces pin usage by arranging the switches in rows and columns. The microcontroller scans the keypad by driving rows low and checking the column inputs. This method allows a 12 key keypad using only 7 GPIO pins, making it very space efficient. So we are using matrix keypad interface in this project. And coming to the next peripheral, that is tactile switches. Tactile switches are simple push to make switches used for user inputs. Due to mechanical bouncing, debouncing delays are added in the software. Pull up or pull down resistors ensure the stable logic levels when the switch is not pressed. And next one is ports and pin configuration. PIC microcontroller pins are organized into ports such as port A, port B to port E. The TRIS register sets the direction of each pin while the port register reads or writes data. For example, setting a pin to 0 configures the fan pin as an output. Next one is switches and keypads. Switches and keypads are the primary user input devices. Tactile switches are used for simple actions like reset, and matrix keypads allow multiple inputs with fewer pins, making them ideal for the embedded systems. These keypads and switches will make it easy for embedded systems to operate. When we create a or when we code the microcontroller, it will be easy when we are using a LCD to code that, or for using it very user friendly, like when we are creating a microwave oven, by just clicking one switch it would change the mode. For that, the switches and keypads are very useful. And next one is CLCD display. CLCD is nothing but a character LCD. It displays text-based information like time and mode status. This CLCD can operate in 8-bit or 4-bit mode. It have control pins such as RS and EN, that is reset and enable, that manage the command and data operations, allowing the real-time user feedback. Next is timers and counters. Timers are internal hardware modules used for accurate timekeeping. In this project, timer 2 is configured to generate periodic interrupts. It operates in registers like T2CON, TMR2 and PR2 to maintain precise timing. And next one is buzzer in embedded systems. A buzzer, it is an output device that converts the electrical signal into sound. In this project, it is used as a time up alert. The buzzer is connected through a transistor to safely drive higher current. And these are the peripherals which we are using in this project. By using these peripherals, the microwave project can be done very easily, very user friendly, and it can be used very easily. Like by clicking one key, it can change modes and it can operate very easily. So coming to the project, microwave oven project overview. The microwave project is implemented using the PICSIM lab simulator. The system supports 4 cooking modes, that is micro, grill, convention and control mode. Each mode is handled using structured firmware logic. And coming to the modes of this project, first one is micro mode. Micro mode is used for normal heating. The user sets the cooking time and the heater and fan turn on. So in this micro mode, first the user sets the cooking time, and the heater and the fan will turn on, and then the LCD display a countdown timer, and system stops automatically when the time reaches 0. Second one is the grill mode. Grill mode is used for grilling the food items generally. The grill heater is activated and the fan runs continuously for heat circulation. The LCD shows the remaining grill time. So whenever the grill time is activated, it will down count and LCD will show the remaining grill time. And next one is the convection mode. This convection mode is generally used for baking and roasting. The user sets the temperature and system performs the preheating. Once the preheating is completed, cooking starts automatically and the status is shown on the LCD. The last mode is control mode, or we can say start or stop mode. So this control mode provides start, pause and stop operations. Start begins or resumes the cooking, pause temporarily stops the system, and stops cancel the operation. This ensures safety, flexibility and user control. So when we are coming to the code and the execution of this microwave project, so here are the execution codes of each peripheral which we are writing. This is of CLCD. CLCD we have written in the C in this MPLAB XID, and next is the interrupt service routine, and this is the code for it, and this is the main thing which we are executing. What are the functions will be defined here, and this is for the matrix keypad which we are using for the entering the key and for selecting the modes and all. This is microwave oven C. Like this is the main thing we are writing coding for everything in this, and this is the coding for timing. And for each code there will be a header file which will be included in this header files. So when we clean and build this, like build is successful. And coming back to the demonstration and showing of the output, we can see here it is the interface of the PICSIM lab, and we already selected the board and microcontroller. So here we can see PIC Genius board and PIC 16F 87A microcontroller, and this is the fan which we are using, and this is the 16:4 LCD which we are using in this. And when we load again, so here we have loaded, and when we start it, so it will be like powering on microwave oven, and then the four modes will be displayed. For example, let's select the convection mode. So first we are convection mode, and then enter the temperature how much you want to enter. Like 23 degrees I have entered, 32 degrees I have entered. So next here we have functions like star for clear and hash for enter, and then when we click on hash, the preheating time will start. So preheating is already set for 60 seconds, so that the preheating is done and the cooking starts again. So for seeing the next functions, we can just reset it, and when we reset it, the microwave oven will start again. And when we see about this micro mode, the power will be displayed, and then we have to set the timer for 2 minutes 3 seconds, yeah, and then hash. So here we are seeing the options, and the time is down counting. We can start or resume the count. Here we can start again the counting, or we can just pause it. We can just pause, and we can stop, or we can just resume it, or we can stop again. And when we stop it, it will go back to the menu screen. And then when we see about this grill also, it is also same like the micro mode. We need to select the time first. So here I have selected 1 minute 3 seconds, and then hash, same functions. So we are pausing it, and then we are stopping it. Pause and stop. Yeah. coming back. So here, the last menu, see the last mode is start mode. So here, the start mode, like it will control, as I said before. So the preset time will be 30 seconds. You can just increase it, or we can start from starting by pressing 4 here. It will go to the 30 seconds plus, and then pause, or 6, like 4 it will start again, and then we'll stop. Whenever we stop, like it will go to the next screen. And this is my project which I have learned. And to conclude this internship helped me a lot. I have understood everything about embedded systems, and I have built my project on my own taking the help of a mentor, which they taught very easily. And the microwave oven project is providing the practical exposure to hardware and software integration. Thank you for your time.